All right, thank you everyone for attending Bryce's seminar. What I'd like to say in this introduction, I think is actually captured in his top right figure there. So this idea of synthetic dimensions is really interesting. You can label anything you want as a site as long as you have an integer to go with it. His sites, as you see there, in that case, are momentum states. And I have to tell everyone in this audience that that is something that I quite honestly had thought would be impossible to make workable. Right, the atoms are going to be moving and flying away. This sounds like a terrible idea for a site, even though you might make the mathematical mapping. So rather than give up on the idea, Bryce has made quite an industry of having fantastic results with this momentum space lattice. So what you'll see today is every single one of his three topics is somehow synthetic. And I think those three synthetics make something that's actually quite real. So I'm super excited to see what new stuff Bryce has to tell us today and other things that I otherwise would have thought to be impossible to do. So I look forward to your talk, Bryce.
Okay, thanks a lot, Ian. Yeah, I appreciate that. Yeah, so I'll I guess for most attendees of the seminar, I guess you're certainly idea of this, familiar with the idea of synthetic quantum matter, maybe studying non-natural materials, whether they're superconducting qubits, trapped ions, cold atoms, and thinking about studying many-body physics with them. And I'll talk a bit about this kind of subtopic today of this idea of generalizing the idea of lattices, where maybe population is moving between positions in space, and generalizing that to this idea where population can move between some other degree of freedom. And Ian's kind of been one pioneer of this field, thinking about population moving between internal states. And I'll talk about some experiments where population moves between discrete momentum states of cold atoms. This kind of ties into a rich history of physics in our field, a lot of which was studied early on in Bill Phillips's group, thinking about things like kick rotors. And then I'll talk about some other directions where we're pushing this, kind of a more strongly correlated system of Rydberg atom arrays with internal Rydberg states acting as sites of a synthetic lattice. And then I'll kind of finish up with sort of a very classical system where we can port over some of these ideas of Hamiltonian engineering with synthetic lattices, but in a really classical regime. So here's a quick outline. I'll kind of briefly give you some introduction of why one might want to use some non-standard degree of freedom as a lattice site and what kind of new abilities that might give you. And then I'll describe these three platforms. So the sort of test bed we've been using synthetic lattices of momentum states, and then some new directions that we're pushing this with Rydberg atoms, maybe potentially molecules, and then mechanical networks. Okay, so I'm going to make this introduction a little bit brief, but I'll try to describe it in the context of Hamiltonian engineering and analog simulation, where if one has a system of cold neutral atoms, I'd say the most optimal strategy for quantum simulation is just to let them do what they do naturally. And that actually gets you quite a bit. So if I have cold neutral bosons or cold neutral fermions in an optical lattice, I immediately get access to a range of physics from sort of early studies of quantum phase transitions with bosons, low temperature Fermi-Hubbard model physics, where one gets emergent magnetism, and one can potentially start to probe questions about whether something like high TC superconductivity shows up already in a simple Fermi-Hubbard model with no disorder, no phonons, none of the things you have in real crystal lattices. However, there's maybe good motivation to try to expand this window of what Hamiltonians one can study by doing a bit of active engineering. And this active engineering can come in different forms. One class of problems that I'll kind of focus in on are kind of quantum Hall physics problems. So maybe trying to eventually get to the physics of fractional quantum Hall states and being able to realize those with artificial quantum matter. And there's a lot of different ways that one can try to approach this. And maybe I'll just say the reason it's hard, if it's not apparent or if you haven't heard it already, is that with neutral atoms, unlike, say, charged electrons, they don't couple to a magnetic vector potential, and they don't naturally experience a natural Aharonov-Bohm phase. but one can mimic such a phase in many different ways. And so the whole game of sort of Hamiltonian engineering for studying quantum Hall physics has been to engineer gauge fields for neutral matter. And so one can take a gas of atoms and try to rotate it very rapidly. Ian developed a scheme based on Raman dressing, where through kind of really ingenious control of dress states, one can engineer artificial magnetic fields and artificial electric fields. And more recently, people have thought a lot about sort of modulating or driving optical lattice systems in some way to hybridize different states to get non-trivial lattice bands. And while I think there's been tons and tons of progress along each of these approaches, and each of them might be able to get to the regime of studying stable many-body states eventually, what's been kind of encountered along the way is that you naturally run into some kind of heating, whether due to off-resonant excitations or some other kind of limitation. And so that just gives you a little bit of motivation to try to maybe find another approach towards studying this kind of physics. And so synthetic lattices or synthetic dimensions are kind of one alternative possible strategy. And so that's a bit of a force motivation for this physics, which can hopefully give you a lot more than just quantum Hall physics along the way. And so as Ian described, synthetic lattices or synthetic dimensions is a really broad kind of catch-all term. And it really encapsulates thinking of kind of any non-standard degree of freedom. So anything that's not just a local site orbital as representing a site of some tight binding lattice. And so here I've drawn a couple levels, 0, 1, 2, 3, 4, with some arrows connecting them. And these levels can represent really anything. And so there's actually been a long history of kind of making analogs between, say, double well physics and spin dynamics. But this idea of synthetic dimensions was really kind of crystallized in the early 2010s by the ICFO group, thinking about how to use internal states to basically enable studies of higher dimensional physics, so 4D lattice physics, and kind of 4D Hubbard model physics. And that was probably the first motivation to try to get access to higher dimensional physics, which wouldn't naturally be relevant in a physical system, where one can think of sort of a combination of real space degrees of freedom, like the sites of a 1D lattice, and then some discrete internal degrees of freedom, like the quantized, let's say, hyperfine states of an atom. And this was really nice, but I'd say the key kind of motivating factor came in thinking about how one can get synthetic gauge fields from this approach. So here I'm going to consider just one atom with some internal states I'll label 0 and 1. And I'm going to think about these as sort of effective sites of a double well. And instead of having some natural hopping here, these states are really, really off resonant if there's some natural energy separation between them. However, if I send in some oscillating electric field, I can maybe parametrically drive some transition. And so here we have some normal dipole interaction with the field. And this directly gives rise to this hopping term between the states. So in the same way that an atom might hop between the left and right wells of a double well, the population can hop between the ground and excited state. And what one gets in this case is that through control of the classical field, you have direct control of this phase that the particle would pick up upon hopping. And by sort of stitching together phases in an appropriate way, Ian and coworkers were able to propose a really direct and kind of robust way to engineer synthetic gauge fields based on synthetic dimensions. And so here one has one real space degree of freedom and then an internal discrete degree of freedom acting as the two directions of the system. And so this was really the killer application that put synthetic dimensions on the scene, because it really helped to tackle what was otherwise kind of an outstanding challenge: how to get artificial magnetic fields without spurious heating. And it turns out that this was really robust. And that's the great thing about a theory proposal, is if it is practically relevant and robust. Yeah, question?
Hi, this is Bill Phillips. Before you go on, maybe you could go back to the previous slide.
Sure.
Why are you calling this parametric coupling?
Because it's resonant. I guess I'm referring to it in that sense. It's sort of weak resonant coupling, and maybe I'm misapplying this term, but
well, I'm not sure either. That's why I asked. I mean, I guess, typically if I thought of parametric driving, I might think of, say, an optical lattice, and I modulate the depth of the optical lattice, and that allows me to make transitions between, say, even numbered space vibrational levels. I wasn't quite seeing that here.
Sure. I mean, here, let's say I have an S and P state, let's say 0 and 1 are S and P, and I have an oscillating electric field, which is providing the same kind of coupling. I mean, it's the same kind of thing. You have some selection rule in a lattice. It's some parity between the site orbitals, and here, presumably something like that is providing some limitation on the transitions you can drive. But same kind of idea that you're kind of overcoming some energy barrier through the frequency of your drive.
Okay.
Yeah, and at each cycle of your drive, you're only putting a little tiny amount of population through. And I think that's maybe a key part that distinguishes these internal state approaches from these sort of lattice modulation schemes, is this separation of energy scale. And that's pretty key. Otherwise, one can actually sort of use the same language with, say, local site orbitals. But I think these spurious heating effects, while technical, they are suppressed in this case because of a large natural separation of energy scales between, say, the motional energy scales of the atoms and the internal energy scales. So yeah, this was a great proposal, and because of this, Ian and also the group of Leonardo Filani took this up within a short time and kind of directly imaged skipping orbitals and chiral motion in these three-leg ladders, these kinds of systems. And so it benefited both from the robust gauge fields that one could generate, and also sort of for free, direct site-resolved imaging along this spin direction, just by performing Stern-Gerlach separation. And this has been extended in recent years to sort of atoms with more internal states. And so recently in the group of Sylvain Nessembene, to sort of dysprosium, I guess here 17 states, where now that you have this extended bulk, you can sort of distinguish cyclotron orbits in the bulk from skipping orbits on the edge. So this is really super powerful. I'd say even at the level of trying to study quantum Hall physics or gauge fields with cold matter, there are luckily maybe still some issues to tackle. So one of them is trying to get strong, relevant interactions in these systems. And it's sort of been a little bit of a conspiracy of nature to some extent. So in these different realizations, the groups were either using rubidium, which happens to have kind of uniform intra and inter hyperfine state scattering lengths. And in the case of alkaline earths, well, one has SUN symmetry. And so what that means is that the interactions, or sort of the total interaction energy, doesn't care about where the atoms are along this internal dimension. And it turns out that you need some mode dependence to get certain kinds of physics that you might want to find in the system. So I'd say that's one open thing still to tackle for this problem. And aside from this one killer application, I'll say that synthetic dimensions also open up a ton of new possibilities for Hamiltonian engineering that don't even have to do with gauge fields in any way. So it really is quite expansive. So the original idea of using them for extra dimensions is still kind of a unique thing that they bring to the table. One can have novel connectivities. And so here one might imagine things like periodic boundary conditions along this internal dimension, where it's normally hard to maybe twist an optical lattice and have it come back on itself. Gauge fields, of course. The interactions, while it may still be begging, I'd say there is the capacity to have some unique forms of interactions in these systems that that look a little bit funny along this internal dimension. They allow for alternative probes, or at least maybe more forgiving probes, like site-resolved imaging and new kinds of spectroscopy. And And then lastly, it also, in principle, just gives you kind of a generic framework that extends well outside of ultra-cold atomic physics. And so to start, within neutral atoms, one has hyperfine states that Ian has kind of pioneered, and a number of other groups have taken up. There are sort of long-lived optically excited states that can be used as synthetic sites that have been undertaken in the group of Junier and also Leonardo Filani. One can use spatial states, so you really can slap this site index onto anything. You can use momentum states. And this actually, from my perspective, this just connected to a large arena of cold atom physics related to things like kicked rotors and pulsed lattices. And this is sort of the low energy extreme of that field of study. One can think about extending this to other systems, maybe trapped ions, or for my interest, things like molecules and Rydberg atoms. So I've worked a little bit on thinking about what kind of many-body states might show up in a system of dipolar spins, where one has many different internal spin states. And our lab has one new effort aimed at kind of realizing this with arrays of Rydberg atoms, where one, instead of driving with lasers, like in this neutral atom case, use microwaves to actually couple together multiple internal states. And there's a new experimental effort, or an effort in the group of Tom Killian, formerly of JQI, with Steve, doing this with Rydberg atoms. And lastly, some work here at JQI with Mohammed and Nito on actually a much probably bigger field of using synthetic dimensions in photonics. And there it actually has real life implications or applications, trying to make things like really good isolators by generating artificial gauge fields and maybe protected one-way transport for photons. And then lastly, let's say maybe there's just one big bin where you reinterpret a whole bunch of things that people have studied for a long time, but perhaps you gain a little bit of insight, or you gain some ideas for new physics by interpreting them through the lens of synthetic lattices. And so this relates to things like multi-frequency kicked rotors, low case systems, dimensionally reduced systems, frequency combs, time bin multiplexing, a whole host of things. Okay, so I'm going to start my talk off by talking about the platform we started with, which is just momentum states of atoms in a Bose-Einstein condensate that are connected to one another through Bragg processes, so 2-photon Bragg transitions. Okay, and I'll talk a little bit about what we've done in the past in 1D and kind of our plans to extend this to 2D, and lose a little bit in terms of control, but gain a lot in terms of the types of tight binding models we can introduce. And then I'll also talk about how interactions kind of manifest themselves in the system. So they've been studied for decades, but maybe they just add something new when you think about them in terms of these synthetic lattices. Okay, so here's a picture of the states we're going to consider for these synthetic lattices based on momentum states. Here I have what's pictured in atomic BEC. I'll think about these as just a source of atoms that start off at 0 momentum. And I'm going to send in a laser with frequency omega plus. And on its own, it doesn't really do anything. So all I'm going to do is maybe have a second order process where I go back to 0, and that lets me trap. If I send in a mirror and reflect the laser, then I'm allowed these different processes that change my momentum, but they're off resonant. And so this is an old result from Trey Porter's group. I think Ian was involved in this as well. You can see something that kind of looks like particles hopping in a lattice of momentum states, except they're off resonant. So they sort of live in this p squared over 2m potential, if you will. And so once they get out to a certain point, their transport becomes off resonant. And so this is sort of the off resonant domain of things like Kapitza-Dirac diffraction. And we're going to instead consider the case where we're actually sending in lasers that are detuned from this big pink one. And the energy mismatch of the photons in these two lasers can take up the extra kinetic energy that an atom picks up if it moves to this state with momentum 2h bar k. Okay. And for the physics process, in the reference frame of the lattice, it looks like atoms are coming in, bouncing off, and undergoing just a Bragg reflection process. And so these states, these momentum states here, I'm going to label them as 0 and 1. These are states labeled by their integer multiple of 2 photon momenta. And we're going to parametrically couple them by sort of tickling them with these laser beams. And we can do this in a phase controlled way. And so extending this beyond just a double well, we're imagining sending in a whole host of lasers from this direction. And in practice, it ends up being quite easy. So these frequency components are separated at sort of kilohertz scale. So this is really one laser with just sort of a comb of frequencies written on it. And sort of in unison, it can drive all these different transitions resonantly. And so the bare Hamiltonian looks like this. You sort of have your p squared over 2m energy of these states. And then you have some complex drive that's time dependent due to all the interference of all these terms. And we do what we would normally do. So you sort of go to the interaction picture, do a rotating wave approximation, and it all gets quite simple. And it's pretty intuitive that we just have if all of these drive strengths are much weaker than the separation of these peaks, you get something that looks like an effective tight binding model where population can hop between the different states. And each hopping term is controlled by its respective Bragg transition and the field that sort of matches that criterion. And so one can control the site energies through detunings of these peaks, and one can control the hopping terms and their phases through the amplitudes and phases of these peaks. And that's basically it. And then you can either turn this on and get dynamics, or do some more kind of adiabatic approaches to try to prepare dress states of the system. Okay, and then in the end, you sort of snap it off. And just like in the internal state case, these states can separate. Here, they just separate on their own. This seems like a bug because they'll do it during the experiment, but it's at least helpful for the measurement. And so this is Alex. I'll use his picture at all times. So now I'll mention that he's off to Honeywell. And so at the end, we may get a picture like this. This has 21 states. And this is sort of at the end of some evolution where we've started on one side of the synthetic lattice and just turned on all the couplings and allowed for something like a ballistic walk of the atoms across the lattice. Okay, so what can we do with this? I won't go into too much detail, but I'll say that you can do a lot. So here I rate it as a 1D lattice, but you can add some extra bells and whistles that sort of go beyond this. So by adding a second lattice, you can make a 2-leg ladder that looks like this, where I actually have unique control over the sort of effective magnetic field or the artificial gauge field through each of these plaquettes. You can do the same. In this case, we actually do it through a second order Bragg process that we add to the first. And it looks like you have a combination of nearest neighbor and next nearest neighbor hopping. This can be mapped onto this interesting kind of zigzag lattice. And you see things like spin momentum locking of the bands. You can partition your lattice in funny ways and actually sort of weakly couple to some reservoir and engineer things like non-Hermitian terms. And then I'd say one of the nice things is that, and maybe I didn't quite make this super apparent, so I'll try to stress it now. Because my states live on this p squared over 2m dispersion, my energy difference between the states varies linearly with which state I'm starting with. And so I really have a unique spectral tone for each of these transitions. And so I can just tune every single parameter of my Hamiltonian. And this allows you to make some really weird types of lattices that would be kind of impossible to make in real space. And so this is actually a model proposed by Jed Pixley and Shriram Ganeshan when they were first working with Dasarma. And so we were able to collaborate with them and then realize it over the past year and also see some nice mean field shifts of the transition points. So this is, yeah, Bill.
Right. Yeah. So I just want to make sure I've understood. Are you leaving the Bragg beams on all the time during this interaction and then just turning them off for analysis?
Yep, that's exactly right. Yeah. So I'd say it really depends on the experiment. Here we do something like, here we do something where we actually tune the parameters during the experiment. We start in an eigenstate and try to track it. But for this one I showed before where the population spreads out, all these parameters are turned on and they're just kept on at some values for some time.
Right.
But
Okay.
we can also tune them throughout and do all the normal bells and whistles.
Right. So one of the things that comes to my mind in thinking about this is that another way of thinking of these things, and you alluded to this before, that these atoms are in an optical lattice. The optical lattice is being modulated. I mean, I think that the kind of thing that you're describing corresponds to the lattice moving back and forth.
It's doing both. It's both amplitude and phase modulation at the same time.
Okay, so yeah, just depends on the distribution of the sidebands.
Yeah.
What you've got, and what that modulation does, which is exactly the same thing as the Bragg scattering that you described, is it makes transitions between different band indices, presumably staying within the same quasi-momentum but changing the band index.
Yep.
And depending upon the strength of the lattice, relative to how far up in the band structure you go, you may not have really a parabolic structure at the bottom, but if you go high enough, you're sure as heck gonna it's sure as heck gonna look parabolic.
Yeah, and there's actually no underlying lattice in this case. So it really starts from something which is free bosons, and then all the different fields that are turned on from that point are sort of small, such that their Bragg-Rabi rates are sort of much, much less than a recoil energy.
Yeah, okay, great. So
but one could think about doing this to a lattice where there it's more like hybridizing bands, and here it's more like creating weird dress states of these bare free momentum states.
Okay, so that was an important part of what I'm trying to clarify in my mind. So the depth of the lattice that's created by the Bragg beams is less than a recoil.
Yeah.
So that means that it's hardly distorted from the free space.
Yeah, this was sort of swept under the rug when I said that we make a rotating wave approximation. So that's exactly the criterion for us being able to do that. Is that if I imagine this as sort of a number of resonances, that they're separated in this case by 8 recoil energies, and so their widths should be much, much less than that to sort of satisfy this unique addressing.
Yeah. Okay.
Yeah. And yeah. So I'll briefly go over kind of one quick example of some new physics that this allows that would be hard to study in a real space lattice. So this isn't quite there yet, but this is maybe a motivation. So here we've studied kind of the simplest topological band structure that one can make. This is sort of what you teach your undergraduate physics students, the Sushri-Verheeger model, where I have tunneling strengths that vary in magnitude as I go across the lattice with a 2-site unit cell. And no doubt we get a 2-band model with a gap halfway in our Brillouin zone, or we can sort of fold this in and get a 2-band model. And the interesting thing happens when you sort of have open boundary conditions in this case, where I can get protected boundary modes at the edge. And I can prepare, so an experiment, I can prepare these states. These are sort of the 1D boundary modes of this SSH lattice. And the nice thing is that even though this is a really simple system, there's no gauge fields, they actually share a lot in common with sort of the quantum Hall states from a big picture, in that they're sort of attached to the boundaries of the system. And if I have a really big 1D system, the modes that live on the left end don't really talk to the modes that live in the right end. And they also don't talk because to do so, they'd have to sort of overcome this energy gap with the bulk. So to have the mode at the left end hybridize with the mode at the right end, we'd have to overcome a big energy gap to the bulk states. And so one thing you might want to do is to sort of add disorder and test the robustness of these states. And so here I've kind of drawn a bit suggestively how these states come about. When the inner cell hopping, these green things are the unit cells. M is my intracell hopping term. T is my inner cell hopping. And when T is bigger than M, I sort of have modes that look like my symmetric and anti-symmetric states between cells, and then these are weakly hybridized by my intracell couplings. And I'm left over with these two kind of dangling states at the edge that are these protected boundary modes. And now I can add disorder to the system and try to eventually sort of destroy these states by some mechanism. And in this case, we're taking a cue from our theory collaborator, Taylor Hughes. This is a phase diagram he had in an earlier paper with a student, Ian Mondragon-Shem. And we're adding disorder that sort of obeys a little bit the symmetry of the system that we're studying. And so this is off-diagonal disorder in this case. And the expectation is that when this disorder strength gets of order the band gap, so here sort of 4 in units of the tunneling, I can unwind these states or destroy my topology and have it go to a topological index or a winding number of 0. And we can measure this. So here we're not looking at them in the same way we did on the previous slide, but we're actually measuring something called the chiral displacement. It's really just sort of the expectation value of where the atoms are on the A sublattice sites. So maybe it's the left ones, minus where they are, what unit cell they're in on the B sublattice sites. And this really starts off quite near 1 for weak disorder up until almost half my band gap. Or sorry, bandwidth. So W is almost half my bandwidth. And then it starts to kind of tank near the expected transition point or crossover point of 4. So that's good. We find fair agreement with the theory. So the solid is sort of the theory for what we actually do. The dashed is funny because it's actually a really long time simulation of 1,000 hopping events on a really huge lattice. And what this is meant to show you is that this transition really doesn't narrow that much. It's kind of a funny random singlet transition that doesn't converge with increasing system size as you might expect for most transitions. And so just to give you an idea of the nature of what's happening here, what should be happening is that first all the states in the bulk are kind of getting reconfigured as I turn up my disorder. And we're doing something called like a float and annihilate transition, just like you have in the quantum Hall systems, where first I'm kind of forming larger and larger bonds across my bulk until eventually I have one that kind of stretches across my entire bulk. And because it has such a long length scale associated with it, it comes down near 0 energy. So it's sort of resonant with these boundary states, and then it can hybridize with the boundary states and destroy the topology of the lattice. So it's of the same kind of float and annihilate transition that you have for quantum Hall systems. And the funny thing was that you can actually, if you kind of inspect the phase diagram here a little bit, you maybe even see something a bit unexpected. We certainly weren't expecting it when we first started pursuing this, that if you start up here in the trivial regime, where I sort of have larger intracell hopping than intercell hopping, and I have no dangling boundary states, as I add disorder to the system, I can actually induce topology in the lattice. And so this is a weird, it was kind of astonishing. The first result mostly just noted it from numerics, then it was explained shortly thereafter by Bienicker's group. And the idea here is that your Hamiltonian, the tight binding Hamiltonian, is effectively getting renormalized by disorder through some higher order processes. And so it's maybe clear if you sort of look at this red line, it's sort of increasing quadratically with W. And the idea here is that my critical intracell hopping, it should be equal to T, the hopping, such that I go across here at M is equal to T. And I'm going to have different contributions that I might get through perturbation theory. I have a first order contribution, which is going to vanish if my disorder is sort of white noise. And then I'm going to get a second order contribution, which will always be positive. And so I'll get a positive shift up. And so for weak disorder, this can push you through to a topological phase. And just one thing to note, there's this constant here, and it turns out that this is only positive if your disorder has the same symmetry as the underlying Hamiltonian. So if I added something like potential disorder, I would actually, which might look like sigma z, I would actually see this tank down. And so that would be something hard to realize in experiment, this off-diagonal disorder. And what we see in experiment in this case, where we can introduce off-diagonal disorder, is that going along this line, we see this mean chiral displacement start low and then kind of creep up in this region here, limited by kind of finite time sampling, and then go back down again as we cross into this Anderson insulator. Okay, and so along with a nice result from the optics community, this was the first evidence for disorder-induced topology and this kind of system known as a topological Anderson insulator. Okay, so I'll spend a couple minutes trying to go over some next prospects for momentum space lattices. And really the next direction we're going to is higher dimensions, where our scheme works great. It's been surprisingly fruitful and robust in 1D, but it's been hard to extend into 2D. And there's a lot of reason to maybe go to 2D, extend these studies of disordered topological systems to things like disordered quantum Hall lattices. That would be fun to pursue, but if I look at my sort of the native energy landscape that we're trying to drive Bragg transitions in, this is something like px squared plus py squared over 2m. If I fix my change in momentum vector delta k, I have a lot of sort of parallel transport transitions that are degenerate. So a number of different transitions that I can't spectroscopically isolate. And so this, you either throw up your hands and say, I can't do anything, which is what we did for a long time, or you say, I'm going to give up having complete control and I can still do a lot of new things. And that's kind of where we're at now. So the idea is we're going to take a lattice configuration, which is pretty standard in the cold atom community. It's what's used to make things like triangular and hexagonal lattices. So 3 interfering beams at 120 degrees mutual separation. And I'm going to drive them in the same way that I do in 1D. So each of these may have some multiple spectral components that can pairwise interfere with the other beams. And what you get is that we actually have a lot of different unique transitions. So here I have solid lines along the sort of northeast direction, dotted lines along northwest, and then dashed lines along the horizontal. And I should think about each of these processes as being independent. And on top of that, I have these different colors, which each have a different Bragg resonance frequency. And so a number of them do repeat. So I have yellow showing up here at 3 points. I should consider that the same exact transition. However, everything else I kind of have full control over. And so the idea is that by controlling the drive field here, I can control which of these transitions I decide to address. And I can also control their strengths and phases and detunings as we do in 1D. And so just by leaving some number of them off, we can make something like a honeycomb lattice or boron nitride. We can make a Kagame or even a dice lattice. These are lattices that have sort of flat bands. Here's just a dynamics with the actual not making the rotating wave approximation of what one gets by preparing different initial states of a sort of synthetic Kagame lattice. Here, the only thing that differs between these states is sort of the phase structure. And let's see if I can, yeah, okay. So in the one case where we've prepared a flat band state, it's frozen. It's frozen. And in the other case, you get kind of fast dispersion across the lattice because you've actually prepared different bands of this 3-band model. And you can even get a gauge fields here. So the basic idea is that we have different transitions contributing to different lengths of this plaquette, and we can have non-vanishing accumulated phase if they hop around the plaquette. And you can even do other weird things like a Lieb-Hofstadter model, and even random flux models, which is allowed. And so this is what we're hoping to pursue. All of this is sort of through first order Bragg, and then if you add some higher order terms, you can maybe get things like disorder, which is otherwise hard to get here. And you can get back open boundary conditions, which is actually sort of lost here, but you can get them back through second order processes. Okay, so in a few minutes, I'll mention atomic interactions. So in this momentum space lattice, I've mostly ignored it, but we do have atomic interactions. These are sort of Bose condensed neutral atoms. And certainly if my atoms are in the same mode, and I have a positive scattering length, I'll get some repulsive interaction U. This is just what you would get between, say, many atoms of a condensate. And if they're in different momentum states, I'll actually get twice that interaction. So I'll have twice the repulsive interaction energy. And the idea here is that for these identical bosons scattering in distinguishable states, I have an additional exchange energy. And if you want to kind of understand this or tie it to something you know, this is what gives rise to the Bogusubov dispersion, why I have an extra energy cost for putting in momentum excitation sort of beyond 1 over the healing length. And so this is not new physics. This is all known for many decades now. However, it can kind of be reinterpreted and give rise to perhaps some new physics when you think about what it does in these synthetic lattices. And so one of the first things we looked at was sort of what happens when you just put atoms in the simplest 1D lattice, and you again sort of do a quench or turn on the tunneling suddenly. If my interactions are weak compared to tunneling, again, just sort of disperse or spread across the lattice. And if my interactions are strong compared to the tunneling, where this U is just the mean field energy, my atoms are self-trapped. And the transition should actually happen when the tunneling bandwidth 4J gets bigger than this mean field shift. And we can do this experiment, look at sort of the same equivalent time here, 1.5 tunneling times as a function of tunneling rate, and see that it mostly looks the same up until some point where things start to break down. And if we look at sort of the accumulated widths, we see good agreement with a simple kind of Gross-Patesky equation here. And the red one includes these off-resonant terms that we throw out with the RWA. I think for time, I'm going to skip over this a little bit. This is just to say we can do block oscillations here as well and see some funny things. I'll mention that we can prepare our atoms not just at a single site, but in maybe a superposition of multiple sites. And we can study the influence of the relative phase between the atoms across these two sites. And so one way to think about this is that preparing this state where I'm in a superposition of two sites with relative phase is like a really gross approximation to a quasi-momentum state. Awful approximation, but it lives somewhere in the Brion zone and not just spread out everywhere. And that I might expect this little wave packet, if I can call something like a group velocity for it, to move as a function of time and to spread out, where it ends up depends on its group velocity, and its spread maybe tells me something about the derivative of the group velocity. And so if I do this for pi over 2, it moves to the right, minus pi over 2, it moves to the left, and for 0 and pi, it mostly just spreads symmetrically. And if I sort of accumulate these data and put them together as a function of phase, it looks kind of nice. We again see this wave packet that flies to the right, flies to the left, and then here at 0 spreads out symmetrically. And now if we look at the average position, which is, we'll call a proxy for group velocity, I see this dependence with phi, sigma, I see sort of one extra peak in the middle. And we can understand these in the weakly interacting case from just thinking about the derivatives of our simple one-band band structure, where it looks maybe at least close to what we might expect. So I have a nearly sinusoidal variation with phi and almost symmetric peaks with phi here when I look at something like the dispersion. And if we turn up the interactions by actually turning down the tunneling, we see things change quite a bit. So these data here for my average position are offset. These ones for sigma are not. And this shows kind of the collapse as we get self-trapped from this spreading to this snake-like structure. But you do see something show up here in the group velocity as well. You see that it becomes very non-sinusoidal. And this is basically, it just pops directly out of this simple, even tight binding model with a Gross-Patesky interaction term. And so this is basically an interaction-driven non-sinusoidal current phase relationship in the system. And I think Bill had pointed out to me that something similar had been seen in a weak link Josephson junction. And I think the distinction is here, it really shows up just because of interactions. And this should be considered as something like an ideal junction in that there's no details of the barrier. It really is just a parametric drive that couples the different states. So, and And I'll say we get a phase-dependent self-trap, which maybe I'll touch on at the end. I'll skip by a little bit here, but I'll say that one direction that we want to push this in is to go kind of beyond mean field effect. So I think this is nice from the perspective of synthetic lattices, because there hasn't been a ton on interactions in synthetic lattices. But to get to the real meat of the problem, we want to study real quantum correlations, because all of this physics, if I can describe it by a Gross-Pitesky equation, it's really classical.
Bryce?
Yeah.
Could you just go back to the previous slide? Yeah, non-sinusoidal thing. What is it that determines which way the asymmetry is going to be?
Yeah, so the sign of the interaction, I think, might change it. I'm not 100% on that.
You mean whether it was repulsive or attractive?
Yes, yeah, whether the U is positive or negative. Although, I mean, don't quote me on that. This is the kind of paper that we analyzed this data a long time ago, and it's been PI limited in terms of looking at it. So it's been a while since I looked at this. Okay. Okay, so the interactions, I kind of describe them in this mean field way, but there really are, you know, interactions that can give rise to quantum correlations. People have used this to study things like four-wave mixing in Bill's group. And the crux here is that because of these this exchange energy, I have cross-mode or intermode interactions that are twice as big as my self-mode interactions. So I have and the main thing here is that I have some mode dependence of the interactions. And it turns out that this, for two modes, can be mapped on to sort of a one-axis twisting Hamiltonian if I think about the effective Hamiltonian for the states of the system. And what can give this rise to? It can give rise to squeezing. So if I start in sort of a coherent state superposition of modes A and B, the interactions in momentum space will just naturally squeeze the state. If you just let them sit there, and as long as they don't fly apart, it will naturally become squeezed because of the difference between self-phase modulation and cross-phase modulation. And so one might hope to sort of use some tricks to keep them from flying apart, some twist and turn schemes, and create squeezing, and then maybe use this for quantum enhanced sensing. I'll say that we've kind of spent the last year or so retooling our system. So we've been changing over from rubidium-87 to potassium-39 to control interactions. We've graduated 2 students. We have 2 new students come on. We hope to get back to BEC soon. I'd say the one last thing that we'd like to get is to just improve or do better at our imaging. So far, we've only really cared about mean populations of the states. We really want to do better. So this is just kind of a bar for what are the state of the arts that people have seen. This is in Menkun Trey's group with absorption imaging. And this is in Fabius Gerbier's group and others with fluorescence imaging. But these are not trapped, sort of time of flight resolutions. And here's kind of the expected scale that we would have for the numbers of atoms we have. And so we think that by pushing quite a bit, we can get to the regime of seeing non-classical correlations in these systems. And what could that open up? With control over the single particle Hamiltonian and the interactions, maybe we could start to study things like correlation spreading or some breakdown in something leading to non-ergodic behavior in this system. Okay, so I think given time, I'm really going to rush through these. I'll say that there's a lot of motivation to move beyond momentum space lattices, or at least push towards systems that are strongly correlated to study things that one can't calculate simply on a computer. So one way to get there is to measure things better in the system we have. Another is to sort of transport some of these ideas to spin systems where you start with strong correlations. And so working with Caden Hazard, seen here with the mustache, and Bhuvnesh Sundar, we thought about how these ideas could be applied to things like molecules and Rydberg atoms, where instead of driving with Bragg transitions, you have microwaves that can drive internal state transitions. And I'd say the key difference is that if you want to be a stickler, maybe you'd like to confine one particle per region in sight. And so you'd like to use systems that have long range interactions. So this isn't a strong requirement, but I'd say it's good if you're thinking about things like chemistry going on or some bad processes going on, which would definitely be the case for Rydbergs and molecules. And so really we're talking about a spin system that has some really weird transverse field that just becomes easier to talk about through the lens of synthetic lattices once you have more than 2 or 3 states. And so some motivations that you kind of start with strong interactions and then add on the lattice and maybe the gauge fields. And nominally, I guess if you freeze motion or have the dynamics and the internal degree of freedom much faster, you don't really care about temperature at that point. So maybe it's easier to observe some subtle phases. And so what does one get for molecules? This is being pursued now in the group of Simon Cornish. One expects that the molecules might spontaneously kind of gather themselves into strings where they sort of nearby in this internal degree of freedom. And this is just sort of the lowest hanging fruit, I'd say, in that it shows up in a simple 1D lattice, and that this could be combined with more elaborate synthetic lattices that one could compose from the microwaves. So while we have a molecule experiment in our group, I don't know that this is something that we're actively looking to study. This is more of a straight QIS experiment, but it's something we could look at in the future as we sort of get to having ground state molecules. This is a project joined with Brian DeMarco, seen here, and students Michael, Garrett, and Eric. We do have a dedicated Rydberg experiment aimed at studying this, led by student Jackson Nganga, and new faculty member Jake Covey has joined on. And so it's potassium-39. We push over atoms from 1 Ma into this chamber. And recently we started loading atoms over the past couple months into a tweezer detuned by about 10 nanometers from resonance, so that's 780 nanometers. And we're starting to see some nice histograms that tell us we have 1 atom. Some recent results from Christian Gross's group doing this in 1064 nanometers. And I'd say it ends up being quite favorable here, actually. While there are some bad light shifts at 1064, we see some encouraging results of doing D1 cooling while imaging on the D2 transition for these single atoms. And so the next steps are to use our Rydberg lasers that are locked to a cavity and drive that transition, and then compose some microwave tones to create these synthetic lattices for Rydberg states. And so this is kind of the picture. You'd have many microwave tones. There's not the simple structure you have for momentum states, but you can find resonances that fit the bill. And you can stitch together a synthetic lattice between Rydberg states. And one would have sort of resonant dipole-dipole transitions between allowed states, so things like S and P states. And you can get a little bit more fancy, use the different P manifolds, and maybe make something that has the ability to put a flux on, so something like a closed loop. And this would be some system that can support flat bands as well. Yeah. Okay, so we're excited by the recent progress, and we have a new grad student, Chenji, coming over once consulates open up, and a new postdoc coming over again once consulates open up in the spring. And noted it before, but just know this Rydberg system, it's maybe easy to accommodate. Once you have Rydberg atoms, I'd say the next thing you need to add is just multiple tones on your microwave. So this is being pursued, and I think there are early results in the group of Tom Killian at Rice. And lastly, if I have a couple minutes, I don't know, Ian or Alicia, how much time is left?
I think we're basically at time, but we need to have food for our after conversation. So you can couch it as the teaser trailer that people should ask you questions about during that. Okay, this is the teaser trailer using ideas from these synthetic lattices to study mechanical lattices, where they offer a lot of possibility. They're not quantum, but you can study cool transport physics. A lot of people are doing this. And you can either use AMO techniques like Raman-assisted tunneling, or you can say masses on springs are classical, damn it, and just use the fact that they're classical and get a little cute about it. So here, because they're classical, we can measure them and actually act on them with forces that depend on their position and momenta in different ways. So here's the basic idea. We measure them, apply forces. This is our thing.
We can tune the frequencies and damping, which looks like sort of real and local site energy terms. We can start off with Qs of around 1,000, then we can actually just cancel damping. We can apply tunneling phases by having forces that depend on both X and P. So this is data where we sort of excite it, have a Rabi oscillation, look in the middle, and here's the canonical case with a 90-degree phase delay because I have a position-dependent force. Here I have a tunneling phase of pi/2, so they're out of phase once they start oscillating. Here they're in phase. This is a tunneling phase of -pi/2. You can see avoided crossings. And the last thing I'll say, because I think this is really cute, you can mimic interactions as well. So you can get synthetic interactions. They're again mean field. But what is a mean field interaction? It's a local density-dependent energy shift that scales in this mechanical analogy with the amount of mechanical energy in the mode. So here we're applying a feedback that doesn't just depend on X, which would be a static shift of the frequency, but one that depends on X squared plus P squared times X. And so this is without the shift. You see some nice dynamics that just look like Rabi oscillations. I'm going to put a little arrow here that ticks like the pi time, where energy transfers between my two masses. Here's experiment, here's theory. Here I've increased the interaction. So we see it get a little weird. Here it gets really weird. We're at an interaction over tunneling of around 3.6. Here is sort of maximally weird. Our interaction over tunneling is 3.99. And then now I've crossed over to some other dynamics where my energy actually doesn't flow back and forth, but it's sort of trapped in one side. And so this is actually just like the self-trapping physics we would study with cold atoms. Here you can study it even in a very, very classical system. And this just reinforces that unless you're studying things like entanglement and correlations, it's all classical. And so we see mode softening as we approach U/4J, and then we actually populate a different plasma branch once we're above that. Okay, so the plan is to scale this up to sort of hundreds soon, kind of scaling down first in size, and then 3D printing and scaling up, and trying to study some weird physics, all very classical, but maybe some interesting lattice systems and interacting gauge theories in these mechanical systems. Okay, and the summary is just these synthetic ideas. They are a bit silly, but they can get you a lot in terms of Hamiltonian engineering. And I'd say the real next step for this field, though, is moving towards strongly correlated physics to really sort of take advantage of all that they give you, but pushing it to a regime where you can't calculate things. Okay, so here's the group, and then here's theory collaborators. For new grad students or undergrads, there's a bunch of new faculty, so I encourage you to apply to Illinois, and then thanks for your time.
All right, so the floor is open for questions. And applause, of course.
Jay, I don't know how to answer things. So yeah, just please unmute yourself.
Oh, hi, Bryce, this is Jay. So looking forward for interactions, I mean, I guess the heating thing that you brought up, sort of, it's at least feels like it comes back, right? I mean, in the sense that you ultimately have a time-dependent interacting system, which presumably will heat up and thermalize. But again, it depends on the rates and et cetera, depends on a lot of details. So can you?
That's right. I would say in our momentum space system, we're kind of just working above it by working at pretty high energy scales. So our J's are rather high. I don't even know if I usually think about a temperature in any sense.
Sure.
Everything happens so fast.
Yes.
And they really are flying apart. So this is sort of some near field description of the physics, as long as they're not in dress states of what's going on. And they will thermalize through one mechanism that I kind of swept under the rug, which is the kind of thing that generates S-wave halos. If you work with BEC experiments, where if I have atoms in different momentum states, as they flow through each other, they'll start to scatter out into these sort of shells that conserve kinetic energy and momentum. And so that's sort of the one process that gives you loss and relaxation if you ignore things like Belyaev damping. And what I would say is that we know how to get a control of that. And so for our experiments on towards squeezing, that kind of process scales like the scattering cross-section. So it scales like scattering length squared. Whereas these sort of forward scattering, or the mean field shifts, scale with scattering length. So it's kind of surprisingly, but as long as you can handle all the other stuff like separation, you win out by working at lower scattering lengths. And it kind of makes sense. Same with sort of light scattering, that one does better and better by working further from resonance, but increasing intensity. And I would say it's kind of a similar thing here.
Oh, I see. So, so there, you're saying that well, what I was worrying about, and maybe I might be just completely confused here, but like basically it seems like, at least in this the first picture on the top right that you have, the synthetic momentum state. I mean, you kind of get this basically this momentum of state, these different momenta states effectively end up becoming flat, I guess, in some sense.
Yes.
Is that right? And then, but it. So what does atom-atom scattering do now in this space?
It would take you out of the mode of states. So I've sort of defined some set of states that represent the sites, and that kind of scattering would take you out of that manifold of states and presumably be lost for all time. So it looks like loss.
So you'd have some kind of lossy, like, let's say if I thought of a fractional quantum Hall of some version, it'd be somewhat lossy fractional quantum Hall state, I guess.
Yeah, so in terms of fractional quantum Hall, I don't know exactly what the prospects for this system of studying that kind of physics is. I would say for maybe things like for studying correlations and how those can change or manifest, for studying certainly mean field things like chiral solitons, I would say this is promising. I think to study things like fractional quantum Hall effect, this is maybe not the system I would start out with. So you can try to do things like confine them along other dimensions, but then it looks very different. I'd say it starts from the supposition that I have a weakly interacting PEC, and yeah, I think a lot of the rules, at least how we describe it, break down.
I see. Okay. Good. Great.
If you go to large scattering for every pair of atoms,
Right. No. Now I understand. Okay. Excellent. Thank you.